Okay, so we've got a mostly conceptual list of questions to talk about today for office hours. We're going to talk about heat transfer, ionic compounds, covalent compounds, and then this whole idea of the universe and entropy. We'll start with, we'll kind of do a chronological order, so we'll, come on in, make yourself comfortable. So we'll start with just this most heat transfer problem. This is a problem that's been around since our first homework assignment, our first quiz, and it's one that people have trouble with. It's a very conceptual question, actually, at its root, but we can also think about it numerically. For me, it's all about, like, what does heat capacity really tell us about? And to think about this, I'm going to do kind of two fake numbers. I'm going to consider something that's like, let's say, 0.5 joules grams degrees Celsius versus, let's do, I want to pick a weird number, 12 joules grams degrees Celsius. It's kind of like, well, what does it mean to have a heat capacity of 0.5 versus 12? What does a small number versus a big number mean in terms of heat capacity? Here's how I think about it. If I've got a beaker that's at 100 degrees Celsius, and inside that beaker, I've got two different pieces of metal. We'll make the green one the low heat capacity, make the black one the high heat capacity. Right? If these blocks are the same mass, but like different sizes, right? So their grams are the same, and they're both at 100 degrees Celsius, then the question becomes, well, which one, when I take them out of the water, when I move this thing out of the water, and I've got this block that's at 100 degrees Celsius, and I do the same thing over here, I take this green block out of the water, and it's at 100 degrees Celsius. Which one is carrying more energy with it? Ideas? Which one's going to carry more energy with it? Green or black? And the way we think about this, since no one's answering, it's office hours, you're supposed to engage more, but the way I think about it is this green block, it only takes 5.5 joules to increase the temperature for each gram. So if these are 1 gram blocks, if it's at 100 degrees Celsius, it's got 0.5 joules for every degree Celsius. Right? So now if I think of, well, how much energy could it lose? It's kind of like 0.5 joules for every degree Celsius. Versus this one is 12 joules for every degree Celsius. So in that way, this material with the higher heat capacity, it takes more energy to get it up to 100 degrees Celsius. But then when I have it at 100 degrees Celsius, it carries more energy with it as it moves. And the difference in heat capacity, there's not a great kind of like heat capacity relates to blah, right? We always experimentally determine it. It doesn't directly correlate with density. It doesn't directly correlate with packing efficiency or like metallic bond structures. It's kind of like all of these ideas meshed up together. It has to do with how well the atoms and molecules can wiggle around inside of the material, and how much energy it takes to get them to wiggle before we start to see that as temperature. So it's going to be the higher heat capacity carries more energy with it. It's kind of the core idea here. Does that make sense? So that means if we have something that's a higher heat capacity, it takes more energy to warm it up, and then it carries more energy away with it. Notice we're not talking about rate here, not how fast does it warm up. Because maybe it warms it faster, maybe it warms it slower. We're not talking about rate. But I have it, and I'm not saying where that energy comes from, right? I've got this is probably on a hot plate, and I'm putting energy into it continually. Once it hits that 100 degrees, the two blocks behave differently. One carries more energy, one carries less energy. The typical questions we see around this, right? We could just do how much water heats up when I drop this block. Like if I take this block and drop it into another thing of water, how much does it heat up? That would be like specific numerical calculations. It's just MC delta T equals MC delta T. Or MC delta T equals negative MC delta T, equal and opposite. Then we have the conceptual questions, which are the things like, everyone scooch in a bit more. Let's scoot you in a bit more. I don't like when people get stuck in the hallway.
Let's put it this way.
You can also have the kind of conceptual questions that come up, which are which one corresponds to the largest temperature change, which one corresponds to the smallest temperature change. So I've got two warm blocks. I move them. I've got which metal, if I heat it up, will give the largest temperature change or smallest temperature change. It's just the biggest heat capacity or smallest heat capacity, right? And it's, when I put it that way, it seems really easy. It's just like, oh, bigger heat capacity, bigger temperature change, right? But it's that kind of deeper conceptual idea of how much energy can a piece of material carry, right? And that's where heat capacity is really a useful number. How much energy can that material carry? And we usually see this for metallic solids. So questions about that before I transition? You're okay. We usually see that for metallic solids because ionic solids behave differently. Remember, one of the things I said in class was the first thing we have to do when we're considering what's going on is we have to think about, is it metallic, is it ionic or covalent? Well, these heat capacity problems are usually liquids or metallics. They're not ionic or covalent. Ionic compounds, covalent compounds kind of behave differently. I guess some liquids are covalent. Most liquids are covalent compounds, but the heat capacity problems are usually pure liquids or metallic solids. Whereas these delta H as solutions, these delta S of universe problems, these covalent, like the covalent solubilities, those fall into a different category of how do materials behave in water. Still looking at this idea of energy transfer to some degree. But we're kind of saying, okay, how do we think about an ionic solid dissolving in water? Right? And, or if we want to make it really broad, we just say, how do we think about one material dissolving into another material? So we're looking at solubility. And we can do this kind of like logic map of, is it covalent? I guess I should do it this way, right? If it's covalent, wait, how do I want to draw this? You know those like yes-no trees that people do? We're going to do it this way. If covalent versus if ionic. Right? If it's covalent, we're going to look at the IMS, and then we're going to have either similar or different. And we can kind of go through this process, saying, well, what happens if the IMFs are similar? In this case, delta H of solution is going to be approximately 0. We call that an ideal solution. In this case, delta H is going to be really big. Positive, if the IMFs are really different. Right, we're going to end up with a big number, and this is going to be non-ideal. Right, in this situation, entropy dominates. Right, because the delta H is approximately 0. In this situation, in this situation, enthalpy likely dominates. Question?
When you said similar and different, are we comparing the solid and solvent?
Yeah, so similar, this is similar IMFs. Oh, I need to give more space for that, right? So we're looking at the IMFs between the solute and the solvent. Right, so I'm doing a shorthand for this. This would be that whole like 6-column table thing we were doing, right? We'd make an entire chart. Like, I'm trying to do it quick to just show you like how my thought process goes. This is not how I solve a problem. This is just how I categorize a problem to start it. So before I start a problem, my brain is doing stuff like this, right? I think, is it metallic? Is it ionic? Is it covalent? At a first glance, do the IMFs look really similar or really different? If the IMFs are really similar, I'm going to be like, okay, that means I have to look at the entropy effects here. If the IMFs are really different, I'm probably going to look at enthalpy. They're probably not going to mix that much. And then we've got a third thing that we can think about, which is what the specific question was for the covalent compounds was, what if a reaction occurs? Right, so one of the things we did in that molecular solubilities lab was we looked at salicylic acid, and we said what happens as we add acid and base to it. And this was something that's a little bit tricky. I warned us about it in class because if we're doing a chemical reaction, the IMFs kind of get scrambled. So we have to look at essentially that one part of the lab, which was just like add acid, add base, is essentially 4 different things we have to think about. We have to think about the IMFs of water with salicylic acid, and actually it's 6 things, and the IMFs of water with salicylic acid. Then we have to look at how the chemical reaction changes the salicylic acid, and now we have to look at the new IMFs with our products rather than our reactants. Say, what's going on with the products with this salicate anion? How does that anion's IMFs behave around water? And so that would be getting into this kind of like doing a detailed thinking about this. Should we go ahead and try that? Okay, so we're gonna take this thinking, we're gonna say, how do we do this for an actual problem? And then we'll go on the ionic train and talk about how we think about ionic compounds. Covalent compounds, ionic compounds. I'm gonna erase this if that's okay. It's recorded too.
Okay.
So for covalent compounds, did you have a specific question? Or?
No, I just wanted to see that.
Oh, okay.
Yeah.
So for covalent compounds, so we're going to look at this thing. Oh, do I know the structure? Does anyone have the structure for salicylic acid? I think it's this. Off the top of my head, I don't know if I trust that, but pull up the lab and see if that's the right structure. Right, so I think these are the 2 structures. Someone tell me if I'm right before I post this to the internet, please. It's in the pre-lab for the solubility 2 lab.
Yeah, looks right.
Okay, cool. Yep, okay, good. Whew. Okay. So here's our 2 structures. And what we want to do is, okay, so we've got this as one option, or if we throw a base on it, we become this. So I want to say, what are, and I'm going to call this, H sal, and I'm going to call this sal minus, just for abbreviations when I make my table. But we need the Lewis structures to understand what's going on. So the first thing I want to do is I'm just going to consider the reactant side, and I want to look at the IMFs of H2O with H2O. I want to look at H-sal with H-sal, and I want to look at H2O with H-sal. And I'm going to look at my London dispersion force, my dipole-dipole, and my hydrogen bonding force. And I'm going to look at how these forces change. How these forces change if I had water by itself, the salicylic acid by itself, and then the water with the salicylic acid. And I want to see, like, is there some benefit to it mixing? Water with itself, London dispersion force, dipole-dipole interaction, hydrogen bonding force. We know it's got all of those. When we look at salicylic acid with itself, looks like it's got the same, right? It's got hydrogen bonding force. It's got London dispersion force. It's actually got a really big London dispersion force compared to water. If I drew a water molecule here, in size comparison, a water molecule would be about like that. Right, so the salicylic acid is a lot bigger than a water molecule. So it's going to have this really big London dispersion force. It's got something weird going on with the dipole-dipole force, right? It's got strong dipole-dipole force and hydrogen bonding force on half of it. Right, over on this half, the dipole-dipole force is usually like across 2 or 3 carbons. So once I get to this other side of the salicylic acid, I've got this whole chunk that's nonpolar. So we've got this situation where part of it is polar and part of it is nonpolar. Right? Part of it's going to interact with water well, part of it is not going to interact with water well. And so that's kind of strange. But it also has hydrogen bonding force. And it's got 2-3 different places where hydrogen bonding force can happen. So that's looking pretty good. When I look at H2 with salicylic acid, I would look at this and I'd say, hey, look, London dispersion force, kind of going to be weird. It's going to go to the smaller one, so the London dispersion force is going to go down a lot because the salicylic acid with its big surface area would rather interact with things with other big surface areas. Still going to have some of it though. The dipole-dipole force, again, is going to only be on half. So that's going to be kind of weird, right? My water molecules are only going to be able to interact with this side of it, not with that side of it. And my hydrogen bonding force, that's still going to be there. So if I looked at this, I would have a hunch. Question?
For the salicylic acid, how do you know that the dipole is only on like half of it?
So this is something that should have been talked about in 124. It's about the extent of like how far the dipole force extends. And we also see it in this lab more when we're looking at these long hydrocarbon chains. And we've got an alcohol here. And we see that there's a certain chain length, there's a certain amount of distance from my electronegativity where the molecule kind of ends up with this half-half effect. And it's usually like 3 or 4 carbons. So once we get 3 carbons away from an oxygen, we don't really see polarization. We really only see polarization in the first and second carbon around it. So when I look at where my functional group is, I look here and I'm like, okay, so here's my first carbon. So I might see polarization across this area. Same thing here. I might see, here's the first carbon, second carbon. I might see polarization across this area. So this side is polarized. This side that's like 4 carbons away, 3 carbons, let's see, 1, 2, 3, 3 or 4 carbons away, that side's not going to be strongly polarized. And so I end up with this weird molecule. It's a little bit harder to see with this big flat structure. It's easier to see with this structure where it's like, oh, you know, these alcohols, it's like that side is polarized. That even might be too far, but it's like the first and second carbon are polarized. The third, fourth, and fifth aren't really polarized.
And then for the H2O with salicylic acid, is it because like only like half of it has like O's that can be bonded to the hydrogens in H2O?
Mm-hmm. Okay. Right. So mostly it's only got half where the dipole-dipole interaction can happen. So if I were looking at this without any other information, I might think salicylic acid would be soluble in water. At least a little bit, right? It's got some good IMF interactions. I've got this weird thing where it's like on half. I would think some would be soluble in water at least. How much did you try to put in water in your lab? I need y'all to talk with me. This is awkward.
Looks like enough to cover the bottom of the test tube. Like.
Okay, so we didn't have a specific one. Let me check something real quick. I'm curious. Let's see. salicylic acid. That's not what I want. I swear. Okay, salicylic acid. I just want to see. There's the Lewis structure. So I'm looking it up on Wikipedia, because Wikipedia has great information. Salicylic acid, you can get like 2, almost 3 grams of it to dissolve in 100 milliliters of water. Oh, sorry, that's in a liter. Well, that's weird units. So it's slightly soluble in water. It's not very soluble in water. And my guess is the reason that happens, we can get some of it dissolved, but not a lot. And that's probably because of this London dispersion force and this dipole only being on half. Right? Essentially, half of this molecule is going to interrupt the favorable interactions that water has with itself. And so, slightly soluble, but not very soluble. So that's one thing to keep in mind. We can get some to dissolve, but probably not much. We see some nice IMF structure interaction. But when we get to these larger molecules, it gets harder to predict. Because you end up with this kind of, like, it's not just yes, no's, right? And whenever we get into, like, out of the yes, no territory, we get to more interesting questions, but they become more difficult to answer. So then we say, okay, that was for our reactants. What happens after we dump hydroxide on it? How's this going to change? So I gotta erase this table and do a new one for my products. Ready for that? Okay. Oh, I don't really need to erase all that. Okay, here we go. So this is gonna be interesting. So we're gonna look at Sal minus with Sal minus. And then we're gonna look at H2O with Sal minus. And we're going to have to add some new stuff onto our table. Because notice, I haven't had to consider ions. But now I've got a covalent ion. Bum, bum, bum. So I'm going to have to look at ion dipole. And I'm going to have to look at ion-ion. An ion dipole is stronger than hydrogen bonding force, and ion-ion interactions are even stronger than that. So Sal minus with Sal minus, great, has London dispersion force, has that kind of like half dipole thing going on again. Technically has some hydrogen binding force. Would have some ion dipole, but here's the thing that's weird. Is a negative ion going to sit next to another negative ion? It's going to have a huge repulsive force. So all of these IMFs that we kind of, in my opinion, naively considered without recognizing it was an ion are all kind of pointless. Because I'm not going to have this negative ion interacting with this other negative ion. There is a possibility, since the negative is all the way over here, there's a possibility that these two, like if I had a second molecule, if this is one of the molecules, and this is the other molecule, let's do it this way, right? So here's one of them, here's another one, right? These are my molecules, it's got the benzene ring, it's got the, here's where the ion is. There's some possibility they could stack with the ions like far away from each other. But there's still going to be that ion force that's going to like push it away. So this repulsive force is going to like obliterate all of these, and they're not going to matter. On the flip side of that, my water molecules, with their really strong dipole interactions, right? Sure, we've got some, this has a big London dispersion force. We got some little London dispersion force. We got some little dipole-dipole interaction on half of it, right? We've still got this polarized hydrogen here. We've got that oxygen up there. We've got some hydrogen bonding force. But now we've got this ion dipole force. And that ion dipole force is going to be this huge attractive force. And so that ion dipole force is going to completely dominate and make it so these things attract towards each other, even though these other things are not, interacting with it really strongly. This ion dipole force is going to pull the waters towards it really well. Stronger than this hydrogen bonding force. So in this case, this ion dipole force is going to overcome any London dispersion force considerations, any of this half dipole force that's going to make it so it only interacts with part of it. The ion dipole force is going to overcome all of that. And so we're going to see this really strong attraction of water molecules to the ion. Question?
So how do you know that H2O with Sal minus will have such a strong ion dipole force?
Ion dipole is always a strong force. It's stronger than hydrogen bonding force.
How do you know that it's there? Because there's like...
it's an ion.
Because it has an ion? Okay.
And it's a dipole.
Okay.
That's it. And so we find, and this is actually a really important detail for not just future chemistry classes, but future classes and just in the world in general. Ionic compounds, a lot of times, like ionic things like this, often like to dissolve in water because of that favorable interaction. Right? Ionic compounds usually like to dissolve in water because of that favorable interaction. So when we have something that is not an ion, we do something to turn it into an ion. We usually are increasing the solubility in that case. Right? Even if the compound was not soluble to begin with, turning it into an ion will make it more soluble. Might not push it to be very soluble, but we will make it more soluble. So we had our salicylic acid that was not very soluble in water because of that, because of the non-polar half versus the polar half. We turn it into an anion, and we've created something that's much more soluble in water because we get that ion dipole force. Is it infinitely soluble in water? No, of course not. But compared to the amount that dissolved before we reacted and the amount that dissolves after we reacted, we're going to see this big increase in solubility. And the fun thing about this, that at least in my classes, y'all didn't play with this nearly enough. You can then, after you make the solid disappear, you can make it reappear by putting H+ in. So you can essentially use strong base and strong acid to decide which form of the structure you have, and you can make it dissolve more or dissolve less. So we get this really cool control, right? So like for me, a lot of Chem 125 and then Chem 126 or 129, whichever one you take if you're taking those, it's finally getting to the point where we get to learn how to control chemical reactions. 124 is like, they exist, good luck. 125, we're like, oh, look, we can use temperature to control it. Oh, look, we can use acids and bases to control it. Oh, look, we can use electrical power. We're not there yet, but we'll get to electrical power to control it. But we start to learn different ways we can actually make the reactions happen or stop the reactions from happening. And we learn where we do have that control and where we don't have that control. There are certain things we can't stop. And knowing what we can and can't stop is really useful, because if you're trying to stop something that can't be stopped, you're wasting your time. So these kind of like chemical controls, these thermodynamic controls, are really neat to me. And this is one of them. So we can change the types of IMFs that we have by doing a chemical reaction. Did that help? I don't remember whose question that was.
That was good.
Yeah, good? Okay. Now, this gets me to a nice point of like, oh, we've made an ion. How do ionic compounds behave in water? Because when we go to ions, we actually, I did this like repulsive. I added these two lines. When we go to ionic compounds, we usually ditch all of that stuff. And what really matters is the ionic behavior, right? Because the IMFs, the ions, the ionic behavior totally dominates over the IMF behavior. And that's why when we were looking at ionic compounds, we didn't talk about IMFs at all, because that ionic behavior dominated over it. So how do we deal with ionic compounds where we've got these kind of considerations, and how do we know how much the water will interact with it? And that kind of gets us to talking about ionic compounds. So, how do we deal with ionic compounds? We're looking at solubility. We're going down this second decision tree, right? We're coming off of the decision tree, and we're like, ionic. In this situation, we're going to look at a couple different things. We could have done it with this other one as well, right? We're going to look at our delta H of solution. And we're going to write it in terms of a delta H of solute plus a delta H of solvent plus a delta H of mixing. This is how we could have done it for either case. We're going to rewrite this a little bit when we're in this specific ionic case. So the case we just did, this would be the salicylic acid with itself. This would be the water with itself. Well, that's supposed to be LV. This would be the water with itself, and this would be the water with the salicylic acid, right? So that was like, my three columns were like these three delta H's. When we go to ionic compounds, we're like, IMFs don't really matter. We can simplify this. This thing just becomes delta H of lattice. And these two get combined to delta H of hydration. And the reason it's nice to do it this way is because it really just lets us focus, and we don't need to think about what's happening with water every time if it's water every time. So in this situation, we can really just think about how much energy goes into breaking apart the lattice, how much energy goes into forming surrounding the ions with water. The lattice always ends up positive, the hydration always ends up negative. And I like to draw this kind of picture to talk about that. What's someone's favorite ionic compound?
Sodium chloride.
That was what I was going to put. I was like, oh, so maybe someone likes something besides sodium chloride. So the delta H of lattice is referring to a specific energy process, right? All of these things are kind of referring to specific energy processes. We're taking our sodium chloride and we're imagining that we're blasting it apart into Na plus gas and Cl minus gas, right? That is experimentally silly, but it's conceptually useful. And then what we're going to do is we're going to surround those things. I got to do a dotted line because I don't know how far down it goes. I think this one goes here. No, I think this one's going to end up here. I'm trying to remember the numbers for sodium chloride. Na plus aqueous plus Cl minus aqueous. So this would be the delta H of hydration. That's always negative, right? The direction of the arrow matters. And this would be the delta H of the lattice. That's always positive. The problem is, right, and I drew that as a dotted line on purpose, because I really don't know how big that line is. I don't know if it's bigger or smaller than my lattice energy. And if you remember, this is part of why we jumped straight to doing experiments with these things. We didn't do a lot of conceptualization. I know both of these things are going to be related to charge density, right? If I have a bigger charge density, then it's harder to break apart the lattice, right? A bigger charge density is a bigger lattice energy. So as charge density increases, that delta H lattice becomes a bigger and bigger positive number. Also, the ion dipole strength increases, right? That's the delta H of hydration. That ion pulling water molecules towards it pulls more water molecules towards it and gets more energy out of pulling molecules towards it. So that's going to make the delta H hydration a larger negative number. This is where it's a headache, right? I don't know which one's getting bigger faster. I know they're both getting bigger. One's becoming a bigger positive, one's becoming a bigger negative. But I don't know which is becoming bigger faster. So I can't really say whether this is exothermic or endothermic just from charge density, which might make you go, well, why are we doing it then? Charge density in this thinking allows us to do this comparative relationship. If I was comparing sodium chloride to silver chloride, I might be able to say something about how the sodium and the silver compare to each other for charge density to get a sense of which one's bigger, which one's smaller. But by itself, it doesn't really tell me much. Which is why, when we first started doing this, we said, okay, cool, here's how we can think about it. Let's do an experiment. Because from this alone, I can't tell. We do the experiment lets me say what's bigger. Once I see that it's exothermic, I know my hydration energy has to be bigger than my lattice energy. But I need the experiment to tell that. Once I see that it's endothermic, if it's a different compound, once I see that it's endothermic, I think sodium chloride's endothermic. Once I see that it's endothermic, I can tell my lattice energy is bigger than my hydration energy. So that experimental information allows me to figure out what's happening in this kind of energy steps of the process. So we really needed experimentation to tell what was going on with that lattice energy idea and that delta H of solution for the ionic compound. Question?
Sorry, but so on the board, is it saying delta H of solvent and delta H of mix are what make the delta H of hydrogen?
Yes.
Does a delta H of solute make the
Delta H of lattice.
delta H of lattice?
Yeah. Because when we're looking specifically at ionic compounds, our solute is always going to have some lattice energy associated with breaking apart that ionic compound. And so we just give it, and again, subscripts are supposed to be useful. We saw that yesterday in class with the different K subscripts for our equilibrium constants. They're always confusing when we first see them. But never ignore your subscripts. The subscripts, once we learn them, they're just these big hints in terms of what's going on. Right? If you see a subscript, you should always be like, why is that a subscript there? Is that useful information? Why'd you put it if it's not useful information? Sometimes, depending on the class, I try to introduce the subscripts when they're useful. Some classes, the subscripts are there and they're like, oh, it's going to be useful later. Don't worry about it yet. But it'll, like, if subscripts weren't useful, we wouldn't put them, right? It's just a waste of ink. So if we're putting subscripts, there's probably a reason. It's supposed to be helpful. And so this, instead of just doing every problem with solute-solvent mix, we change the subscript to kind of communicate what kind of problem we're working on. Right? As soon as you see that delta H lattice, you're like, oh, an ionic compound falling apart in water. Right? It gives you that hint. If you saw delta H solute, delta H solvent, delta H mix, maybe it's covalent compounds, maybe it's ionic compounds, we don't get that extra information. But as soon as we see delta H lattice, oh, we're breaking apart a crystal structure. It's an ionic compound, probably. So, helps us. Yeah?
Sorry, I know you went over, but could you say again why charge density is important?
So charge density gives us this idea of magnitude of how big these things are going to be. Right? I know that the lattice energy increases with charge density. So as charge density goes up, lattice energy goes up. So that means if I had multiple compounds on a list that I wanted to compare, I know there's some homework problems like this, I could say from the charge density, from my periodic trends in 124 of charge and radius, I could say which one has the biggest lattice energy. Also works for the hydration energy. If I had a list of compounds, I could say which one is going to have the biggest hydration energy, the biggest negative hydration energy, by looking at the charge density. So we get that kind of little bits of information there.
And why again does charge density not have an effect on delta S lattice?
Ooh, that's a great question. We'll move on to delta S lattice with this one, because I think that'll get us to, I thought somebody wanted to do the lattice with the delta H, delta S, delta G's of these. I didn't write it down. I feel bad not writing it down. So that's delta H lattice, but should we do some entropy for this as well? Are we ready to try entropy? Questions about this before we go on? Okay, so how does this change if instead of looking at delta H, we're looking at delta S? And technically, I can just do this. I can just switch all of those. You should rewrite this in a new part of your notes, but I would have to erase everything and write it again. Right? I can just do this with the exact same process, thinking about a different thermodynamic variable. So instead of thinking about enthalpy, which is a thermodynamic variable, I'm going to do it in terms of entropy. My process, my Hess's law thinking, will still have me doing the same steps. I'm still going to go up, I'm still going to go down, But now instead of looking at hydration, I'm going to be looking at entropy. Sorry, hydration. Instead of enthalpy, I'm going to be looking at entropy. Here's the place where it gets quirky and where entropy behaves a little bit different than enthalpy. And when we see it, it totally makes sense. But if you don't slow down and think about it, it just is like something you feel like you have to memorize. And it's like, if we're doing chemistry correctly, like there's very little you actually have to memorize. The things you memorize are usually because you use them so much. Like, what's the heat capacity for water?
4.184 joules.
Did I tell you to memorize that? No, you just use it so much it sticks in your head. Why do I know so many chemical compounds? I just use them so much it sticks in my head. Why didn't I know salicylic acid's Lewis structure right off the top of my head? I only use it when I teach Chem 125. So I don't use it that often. The only reason I remembered it is because we did it like last week. So it was like in my head a little bit. So in this case, we say, okay, we could memorize that it doesn't affect it, but let's think about the reason why. Fundamentally, entropy is like a number of microstates. So when I go from a solid to gas particles, that's going to be a big increase in microstates. Does the number of microstates care if it's a +1 or a +2 or +3 or +4? Right? If I did this for sodium chloride, or if I did it for barium sulfide, which would go to barium 2 plus gas plus S2 minus gas. Right? In that situation, right, whether I'm looking at sodium chloride or barium sulfide, the lattice energies would definitely be different. Because the +2 -2 is going to hold together stronger. It's going to take more energy to push them away from each other. But when I'm looking at entropy and I'm just like, how many particles are there that can rearrange? I've got one thing going to 2 gas particles. I got one thing going to 2 gas particles. That idea of charge density does not affect the lattice entropy. Because all I care about for lattice entropy is how many things are there as it breaks apart. How many different microstates, how many different ways can I arrange it? Everyone scooch in a little bit more. There's space up here too. As one person comes out, everyone just gets in a little bit more. So when we're looking at delta S lattice does not have any charge density dependence. But when we look at hydration, right, hydration is this idea of the water molecules interacting with the ions, ion-dipole interaction. Here, if we have a Ba2 plus aqueous plus an S2 minus aqueous, what's going to interact with the dipole moment of water better, a +1 or a +2? +2, right? That stronger charge, that charge is going to give that stronger interaction. So delta S hydration does depend on charge density. As charge density goes up, that hydration entropy becomes a bigger negative. Right? Because those water molecules are going to be attracted more. They're going to organize around the ion more. That organization around the ion is going to give it less and less microstates. A bigger decrease in our number of microstates means that delta S is going to become a bigger negative number. And this gives again, going back to why is charge density useful, right? By itself, charge density really doesn't tell me much about sodium chloride versus barium sulfide. It doesn't tell me about sodium chloride by itself. It doesn't tell me about barium sulfide by itself. But when I want to do a comparison of the two, that's where charge density becomes useful. I probably should have picked something besides barium. It was just the first thing that popped into my head. But barium has a really big radius. So that's going to mess up the charge density. I probably should have used magnesium. I'm going to just do one switch to make it less complicated. I'm going to look at magnesium sulfide. Just because I don't want us to worry about charge and radius at the same time yet. So if instead of barium I used magnesium, right? Cool. Right. So same thinking, right? Having that +2 charge right? The reason I did this is sodium and magnesium have about the same radius, so it's really just the charge, right? In that situation, we can see that the magnesium is going to pull more water molecules towards it. It's going to decrease that number of microstates. So in a comparative way, charge density helps us out. If I was just looking at sodium chloride, charge density doesn't help me out. It's that comparative place where charge density helps out. Same thing we saw with the delta H's. Yeah.
So also for like the entropy of hydration, like there's an increased charge density, the entropy of hydration increases, right?
I want to be careful about the word increases because some people hear increases and they think it moves more positive. Mm-hmm. The entropy of hydration becomes a larger value, and it's a larger negative value.
Right, and then so does the delta S of lattice energy also increase, so it creates that imbalance again?
Well, what do you think?
I mean, I would assume not, but
why not?
Because if it increased the entropy of the lattice, then I don't know. I guess like in my mind it would dissolve more.
You're right, it doesn't. And the reason it doesn't is because when we're thinking about entropy, right, I'm going from a solid to a gas with no other interactions, right? And I picked these cases in particular. So I'm going from one solid to two ions, or I'm going from one solid to two ions. In terms of number of microstates, that charge doesn't affect the number of microstates, right? They're gas particles flying around. All I care about is the number of particles. So if I did something like magnesium chloride where I ended up with even more particles, it gets a little bit more confusing, but that's why I picked it this way as a simple example to start with. So for the entropy of the lattice, we get no charge density dependence.
So does the delta S of hydration, like increasing, does that tell us anything about like it soluting or like dissolving? Or like what's the like
it allows us
benefit
to
of
say
knowing that
so
the delta S of hydration increases with partial charge density?
Well,
charge density.
Yeah, so it allows us to do that kind of comparative thing. So we can tell which thing is most likely to have the largest positive delta S of solution, which will get us at which one dissolves more, right, at a particular temperature. So again, it doesn't tell us things about the compounds by themselves, but allows us to do this comparative type thinking of which one would be biggest, which one would be smallest. And since we know that it's not affecting the delta S of lattice, right, as long as we're comparing things that are going to two ions, we can figure out, like, I can tell from this that sodium chloride is going to have a larger, is more likely to have a positive delta S of solution. And magnesium sulfide is likely to have a less positive delta S of solution, maybe to the point where it's completely a negative value. And it turns out magnesium sulfide doesn't dissolve in water very well, but sodium chloride does. And that's going to be taking these delta S ideas with the delta H ideas to get those delta G ideas. But if we just tried to do delta G all at once, right, the whole reason we're breaking these things down into smaller and smaller considerations, is it ionic, is it covalent, is it delta H, is it delta S, how many steps can I think about it in, is because chemistry is complicated. Right? There's a lot of things moving around, there's a lot of different possible interactions, and we're constantly just trying to turn it into smaller, bite-sized thinking pieces. One of the problems one of the challenges that we all face in learning chemistry, I faced it, I still face it, you're all facing it, is taking those bite-sized chunks that are easy for us to think about and putting them back together to figure out what we were just trying to digest. Right? We get these little pieces where it's like, I know how this piece works, I know how that piece works, I know how that piece works. But do you remember how they all go together to describe this larger kind of concept of what's going on? The whole reason we're doing this like picture in this delta H's and delta S's is so we can have a better way to predict whether solids dissolve in water or not. And if we get too caught up on these like little details, we forget about that bigger picture.
So if I were to put this in like a general statement, it would be the larger the charge density, the larger the negative delta S hydration, which means the delta S of the solution is more likely to be negative.
Yes.
Okay.
I would add some place in there like in a comparative way. Right? It doesn't, if I just have magnesium sulfide by itself and I'm like, it's got a big charge density, it doesn't let me say much about magnesium sulfide by itself. It's a comparative tool.
Okay.
So as I'm looking at different solids. And this was the place where we practiced this. If you remember that in the Solubilities 2 lab where you had that big grid of all the different things you put down, the cobalt compound that was a +2 charge in a small radius made more precipitates. Because it has that higher charge density, so it's got that bigger delta H of hydration, that bigger delta H of lattice, and that more negative delta S of solution. Those things together make it less likely to dissolve. And so that's taking those little bite-sized pieces and being like, how do I put this all back together? And that lab was supposed to help us think about those different things. Question?
So when you were explaining why the entropy of hydration is more related to charge density, you said that it was more similar to water, or did I mishear that?
No, it was because the hydration process is water is being pulled in and organized around the ions. So as more water, a higher charge density can attract more water molecules, and that more, we talk about it, the technical term we use is the size of the solvation shell. So it turns out that an ion gets a little shell of water around it. And the higher the charge density, the bigger that shell of water around it. And that larger solvation shell creates a bigger decrease in entropy.
Okay.
So it's the way that they're interacting with each other.
That makes sense. Yes.
Cool. Other questions about this? Did anyone? I might be remembering incorrectly. We can watch it in replays. But did someone? I'm kidding. We're not going to do that right now. Did someone have a specific question about doing like the delta G, delta H, delta S for an ionic compound, or am I confusing that with the S universe thing?
I think you're confusing
Okay, cool. Other questions about this idea of delta H as solution for ionic compounds and lattice energy? We already did the covalent compounds. I did that out of order a little bit. Let's go ahead and look at this idea of delta S universe. This is 3.2 number 11. I'm going to erase everything that's here. Does someone have that handy?
I think that's for an endothermic spontaneous process.
Okay.
And then it was like find delta G, H, and then system, surrounding, and universe of entropy.
Right. So kind of a funny thing is, asks us to find delta H, asks us to find delta G, and then for delta S, it gives us 3 delta S's that it wants us to find. I'm going to take off the standard here. Right? And that's because entropy, if you remember, the whole time I've talked about entropy, I've always said, is conceptually difficult and experimentally difficult. It's kind of a hassle. Delta H, if it's endothermic, we can tell delta H is greater than 0. If it's spontaneous, we can tell delta G is less than 0. And every time we've been doing delta H's and delta S's, we've always been doing it for the systems. And the delta S that I usually care about is the system. To get at the kind of core idea of how entropy can be, if delta H is positive, delta G is negative, delta S has to be positive, right? Because we can have delta G equals delta H plus T, minus T, delta S. Right? If I know that it's spontaneous, I know this is negative. If it's endothermic, I know this is positive. The only way that's possible is if delta S is also positive. Right? And so that's the part that we really focused on in class. And then we've got this bit about the surroundings and the universe. And this is kind of a weird thing. It's very important in physics. It's very important in our upper division thermodynamics classes. It's kind of like part of this core idea of entropy and this idea of microstates. It's this combining of what's called the second and third laws of thermodynamics. And it pretty much says, look, the delta S of the universe is going to be equal to the delta S of any system we're looking at plus the delta S of everything else around it, what we're going to call the surroundings. So for example, if this pen was the system, the surroundings would be everything else in the universe besides this pen. Kind of a weird way to think about things, right? If this whiteboard was my system, the surroundings would be everything else in the universe besides this whiteboard. And the reason they think about this is because it really is this idea of, for me, it's this core idea that I talked about in different terms. But it's this idea of why does energy spread out, right? When we have that hot piece of metal and we put it into a cold thing of water, why does the hot metal cool off? Why does the cold water warm up? And energy dissipates. And how do we describe this? Like, we're all comfortable with that. We see it happen all the time. If you touch a hot piece of metal, you burn your hands. You never touch a hot piece of metal and freeze your hands, right? You never hold a cold piece of metal and it gets colder, right? There's like this flow of energy that happens where energy dissipates. And how do we, from a standpoint of energy, describe that happening? How do we explain that happening in the universe? And the way they do this is they say, look, the delta S, the first thing is Boltzmann introduces this idea of microstates, the way that energy can organize. And the other thing is we say delta S of universe has to be greater than 0. For any process that's going to happen, delta S of universe has to be greater than 0. Our system and our surroundings could be positive or negative, negative or positive, but they have to balance out so that the universe ends up overall greater than 0. Which means energy's always going to spread out more and more and more. This idea is what makes it so energy dissipates, really. Right? We always have to be increasing the number of microstates in the universe as a whole, which means on Earth, if Earth is our system, we can create order on Earth as long as someplace else in the universe, we can create higher energy density, right? Fewer microstates on Earth as long as energy is dissipating someplace else. Question?
So for a reaction at equilibrium, is delta S of the universe equal to 0 or not?
So there's notation in the textbook that I am not a fan of. And they do a kind of funny thing where they try to relate the entire universe to whether a process can happen or not. And I'm not a huge fan of that table. I know the one you're talking about. They do this, so this is spontaneous. They say delta S universe equals 0 would be equilibrium. And then they say delta S of universe less than 0 would be non-spontaneous. I would use different language for it. I would say, rather than calling this spontaneous, I would call it possible and impossible and on the border. Right? Rather than calling it spontaneous, non-spontaneous, and equilibrium, I would call it something that's possible, something that's impossible, and something that's on the border between possible and impossible. So I would use slightly different language. I would use spontaneous, non-spontaneous, equilibrium if I was talking about the system, not the universe. And so their notation is not technically incorrect, but I find that it mixes some language that I use in a particular way that the authors of the textbook don't use as particularly as I do. Does that make sense?
Yeah.
So they're kind of using the term equilibrium to be like it's on the border between spontaneous and non-spontaneous. They're using the word spontaneous to say it's possible, and they're using the word non-spontaneous to say it's impossible.
Okay.
And At least that's the way I'm interpreting it. This statement here, delta S of universe is always increasing, is like a fundamental law of thermodynamics. So I like that one. Now, the other funny part here is essentially if our system is greater than 0, whenever this is positive, this is negative. Whenever this is negative, this is positive. Right? Any effect that I have inside of my little system, my surroundings are going to behave in an opposite way. Kind of like an equilibrium idea, right? It's going to try to balance it out. It can't perfectly balance it out. In this situation, if my system is increasing its microstates, dissipating energy better, the surrounding's going to do it a little, like that minus has to be smaller than this positive. If the flip is true, if my system is decreasing its microstates, it's getting less entropy, then the surroundings that positive has to be bigger. So, in terms of this problem, and I didn't talk about these things that much. I was like, you can just read it in the textbook. For me, they're not core, and they're not core to what we're doing in the class. They're fundamental to the idea of entropy, second law and third law of thermodynamics, but they're not core to how we're using it. We're really just looking at delta S of system this quarter. So in this problem, if we're doing delta S of surrounding, because my system is positive, my surrounding has to be negative, and my delta S of universe always has to be positive. You don't seem happy.
No, I was reading it.
Okay.
Because it's endothermic, that means that there's an input of energy, which is why the system is positive, right?
The delta H of the system is positive, yes.
Yeah, that makes sense.
Other questions about this? There's another problem that does this that has like water boiling that I think is pretty interesting.
Like 80 degrees.
Yeah. Question?
Yeah, you said that, or at least I think you might have said this in class too, that delta S is 0 when delta G is 0 when it's at equilibrium. Did you say?
No, delta G is 0 at equilibrium. Delta S is not 0.
Okay.
Delta S is almost never 0.
Okay.
I'm trying to think of a situation where delta S would be 0. It'd be like a weird coincidence. It'd be very unlikely. Delta G, since delta G is kind of this overall energy that's pushing us, we got to be careful with our language, right? We did a big switch in class yesterday where we switched from this idea of spontaneous and non-spontaneous to towards products or towards reactants. How are we energetically balancing the entropy and enthalpy of our reactants versus the entropy and enthalpy of our products? We're using delta G and then shifting it to KEQ so we can talk about that idea. So if we have delta G is equilibrium, that's the kind of balance point between it being towards products or towards reactants or spontaneous, non-spontaneous, or possible, impossible, depending on which system we want to think about. So that delta G being 0 is kind of that balance point. We're usually interested in it because of that idea of having controls. Right? If we can get the delta G to be a 0 point, we can figure out how can I tip it one direction or the other. And that means how can I use that information to turn a reaction on or turn a reaction off. Make it start to happen or make it stop to happen. A great example of this is protein oxidation. How can we slow down or stop protein oxidation? I'll give you a practical example. How do you keep your meat from going bad? You put it in the freezer, right? Protein oxidation is what causes food spoilage, right? It's oxygen interacting with the different molecules. The molecules break down. Instead of being the protein, the things we want, they become these smaller molecules that smell funny and taste terrible. How do we slow down that reaction? Put it in a freezer. You can almost completely stop. If the freezer is cold enough, you can pretty much completely stop the reaction. And you can keep your food from spoiling for a really long time. The process, if you get it too cold, will also damage some of the other molecules that are there. And so it might make the flavor not as good, it might make the texture not as good, but it won't spoil. That's useful, right? What happens if we heat up, right? If we go to a really high temperature, we can cause a protein reaction in a different direction that cooks the food. So we're using temperature. We use temperature all the time, like cooking food and why do we put food in the refrigerator? We're the refrigerator's slowing down reactions rather than stopping them, but we're less likely to damage the cellular structure of the material, right? Like, have you ever accidentally frozen lettuce? It's horrible. If you got an extra piece of lettuce, throw it in the freezer and then thaw it out and see how terrible it is. The water freezing shatters all of the cells. So you can freeze lettuce and stop it from spoiling, but you turn it into a mushy thing, and it's not very pleasant to eat. Still got the nutrients though, so. Okay, so there's different reasons why we use a freezer versus a refrigerator. But it's this idea that we have some control over whether chemical reactions happen or not. I like food, so I'll use a lot of cooking examples. I teach stoichiometry by saying, pretend it's a recipe. Speaking of food, should we melt some ice? I don't know why that's speaking of food, but I like to think of these ice melting problems kind of in like making ice cream and ruining your ice cream. But other questions about this before we go to an ice melting problem? Okay, do me a favor, whoever has a particular, like you each probably have a different ice melting problem in mind. Someone pull up an ice melting problem so we can do one.
I have one from NP 1.2. It's question 7.
Said from 1.2?
Yeah, 1.2.
Cool. Okay, let me erase the board and then we'll get that going. If someone wants to move into this chair, you can. You bet. See ya. You don't all have to stay on the floor. Otherwise, it's just like awkwardly this empty chair in the room. People sitting on the floor. Okay, so we're looking at MQ 1.2, number 7. Is that right?
Let me make sure it's number 7. Yeah, number 7.
Great. What's the problem saying?
Okay, so the problem says, okay, so a 78 gram, oh wait, sorry, this isn't the ice one, sorry. Number 9 is the ice one.
Okay,
sorry,
switching to number 9, no worries.
So a 56 gram piece of ice at 0 degrees Celsius is put into 123 milliliters of 60 degrees Celsius water in an insulated cup. Does all of the ice melt? What is the final temperature when everything is in equilibrium? How much ice is left when everything is in thermal equilibrium?
Okay, so I want to find out how much ice is left, what's the final temperature? My hunch is, just by looking at this, all the ice is going to melt, right? I got a lot more water than ice. I know the heat capacity for water is really big, but I'm really not sure. So the first thing I'm going to do, the first thing I have to check is, does all of the ice melt? So what I'm going to calculate, I did this, someone asked me a question about this earlier today, and I kind of came up with this new way to think about it in terms of what's my limiting reactant? Is my limiting reactant hot water or ice? So what I'm going to do is I'm just going to calculate max ice melt. I'm going to calculate the maximum amount of ice I can melt. That's going to be this thing. That's going to be 123 times 4.184 times, I would go all the way down to 0 if I'm doing my maximum. And that would be equal to negative n delta H. That would get me my max. Where I know the delta H, I'm just going to put it in joules, is 6010 joules per mole. So this would be my water losing as much energy as possible to figure out how many moles of ice I could melt. So I do this calculation to figure out my maximum ice melting. I'm going to calculate an N value. I'm going to do 123 times 4.184 times 60 negative. And I get negative big number. I'm going to divide by 6010 negative to get 5.137 moles. I'm going to multiply by 18 grams per mole. And I could, at maximum, melt 92.5 grams. Do I have more or less ice than 92? Right? My ice number is smaller than 92. All of my ice is going to melt. Not only is all of my ice going to melt, I'm going to have leftover energy. That leftover energy means that if I'm looking at this in terms of energy curves, all my ice is going to melt and it's going to warm up some while my hot water is cooling off. Right? And these two things should end up at the same T final. So all of my ice is going to melt, and then I'm going to have some leftover energy. I'm going to have, this is going to be a weird way to say it, I'm going to have about 40 grams of leftover energy. 40 grams of ice melting is leftover energy. So once I know all of my ice melts, now I can set up my problem. Because before I figured this out, I could have had this situation where this thing goes all the way down to 0. If that goes all the way down to 0, then my N can't be the whole amount. So I have to figure out which situation I'm in before I can finish the problem. Once I know all of the ice melts, then I can go ahead and set up my problem. Is that part clear? That's the part that most people struggle with. That's the part that's hardest for folks, is figuring out does all of the ice melt or not. People always want to jump straight into doing like MC delta T equals N delta H because that's what we always do. It's like, whoa, hold on. We have to first figure out, are we in an MC delta T equals N delta H, or are we in an MC delta T equals N delta H plus MC delta T, right? How many different Q's am I going to have in my situation? That's the analysis part that people usually struggle with. Once we do that analysis part, then it becomes pretty easy. I'm going to erase this bit in blue. Are you ready? Okay. So now that we know all the ice melts, now I need to calculate my T final. I know my ice remaining is going to be 0 grams. All of it's going to melt. And now what I can do is I can think about this in terms of like Q1, Q2, Q3. I'm going to have energy leaving my hot water, going into my ice and warming it up. So I'm going to have, for the melting process, I'm going to have an N delta H. For that warming up, I'm going to have an MC delta T. And then for that cooling off, I'm going to have an MC delta T. I have to be careful. I know it looks a little silly right now because I've got an MC delta T and MC delta T. I should just subtract it, but those are different. I'm going to label it like water, water, water. Let's say it's warm, warm, warm. That's the warm water. I just don't feel like writing 2 W's. Question?
So that's the Q for the ice reaching melting point, and the Q for the ice melting, and then...
It's already at melting point. So it's the
Okay.
Q for the ice melting and then warming
Right,
up.
Okay,
You're thinking of a different problem where we had to warm it up and then melt it.
okay.
There's a really complicated problem that has 5 different Q terms in it. That's not this one. This is only 3 Q terms. I think it's plenty. Now I start plugging in numbers that I know. This is going to be 56 divided by 18 times 6010. I'm converting into joules. My MC delta T is going to be 56 times 4.184. Right? This is the melted ice warming up, so I use the heat capacity of water. The delta T is going to be some T final minus 0. And then I'm going to have my water, which is going to be negative 123 times 4.184 times T final minus 60. Sorry, I'm scrunching at the edge of the board there. Let me fix that a bit. That bothers me. Equals negative 123 times 4.184 times T final minus 60. There we go. Okay. So at this point, y'all can do this calculation, right? Like this, at this point, it's easy. And this is one of the traps that people get caught in when they're working on problems with me, or working on problems with a tutor, or working on problems with, they're studying with people. If you've always got somebody doing like the hard part of setting up the problem, and you're just punching stuff into your calculator, you're always skipping the hard part of the problem. And so when you sit down to the exam, I know our exam's tomorrow, so it's a little late for saying this. Then when you sit down to the exam, you look at a problem, you're like, I don't know how to start this. Let me go to the next one. I don't know how to start this. Let me go to the next one. I don't know how to start this, right? Starting the problem is always the hardest part. If you've got one thing you're going to practice between now and tomorrow, don't do the whole problem. Just practice the setups. Practice the setups. Practice, like, can I read the problem and figure out what it's trying to get me to do? Can I write down the equation that this problem's talking about? I'll go plug in the numbers and use my calculator later. Right? That's always the slowest part. It's the thing that's really actually difficult, is how am I thinking about this, and how does that set up my equations? Because once I give you this, we're just doing math. Question and question.
So because there's more energy released by the water to melt the ice, that's why, like, once it melts, it warms a little bit more because there's that more energy.
Exactly.
Okay.
Right. So it warms a little bit more.
Okay.
Right. And because there's extra energy, and there's still in thermal contact.
Okay.
So if you remember that, like, the first week of class where I had the Ziploc baggie of ice, and I put it in until it melted, I pulled it out, and the water was cold still in the baggie. So that, I stopped it from being in thermal equilibrium. That's harder to do unless you've got it in a Ziploc baggie. I'm trying to think of a funny thing. So if you poured water into like an aluminum cup and then put it into a container with ice, you could keep the ice and the hot water separate from each other. And you could figure out how much hot water, that would be a really interesting question. It's too late for me to write a question like that. But it's how much hot water would you need to melt a specific amount of ice and not warm it up past 0? That'd be funny. Maybe I'll create a question for that in the future, but that's not an exam. It's just an interesting problem. Question, yeah. Oh, and you have one too. No, you go.
The 60-10 for delta H again?
This 60? Oh, this 6010?
Yeah.
That's off the equation sheet, right? That's the delta H of fusion for water is 6.01 kilojoules per mole.
Oh, okay.
And I just converted it to joules.
Okay, perfect. Thank you.
And then you had a question?
Mine was like kind of question, kind of like asking it this would be accepted. Because the way I solved it, instead of doing this, like at the end, what I did was I didn't put it into moles of how much ice would be melted. I just checked like how much energy is created from each one. And then I obviously the water was larger, so it melted the ice. So then I subtracted their energies, and then I just did like what the temperature final of the melted ice water would be.
Yep, that does work. You're essentially... What was that? Oh. That is a totally fine way to do it. We're about to do that inside of this problem if we keep going. I'm not a huge fan of framing my thinking that way because it kind of separates the physical process from the math to some degree, right? It works mathematically, but it kind of gets me out of thinking about the energy flow. And thinking about the energy flow is a really important part of this for me. The place where you get to that is when I do this 1, 2, 3, when I do this multiplication times 60, that's going to give me my maximum energy. It's going to be the same number we saw before. Right, so when I do 1, 2, 3 times 4.184 times 60, this is going to get me negative 30878 joules. And I'm going to do 1, 2, 3 times 4.184 and 514.6 Right? That number in joules I have there, that number in joules is the maximum amount of energy that the water can lose. And so when I put that in comparison with this is the difference you're taking, right? 56 divided by 18 times 6010. There's 2003 joules, right? When I take the difference between those two, that's going to be my extra energy. So we end up doing the same thing mathematically. It's just how do we frame our thinking?
So like if I did that on the exam,
You'd get credit.
okay.
It'd work. If we do something slightly different on the exam, where we change the cues a little bit, that's where it gets into being trouble.
What do you mean change the cues?
Like if we introduced a chemical, or like I'm thinking about other problems we've had on the homework. If we introduce the fact that the ice doesn't start at 0 degrees, if we introduce the fact that instead of just being hot water, there's a chemical reaction as well. If we introduce something besides ice, so like if it was instead of ice, it was like I'm trying to think of another thing that would melt in water.
That's kind of like
If it was gallium, gallium would be a cool example, right? Gallium is a metal where its melting point is like 92 Fahrenheit. I know its melting point in Fahrenheit, which is pretty silly. It's the only compound I know the melting point in Fahrenheit. That's because a piece of gallium sitting out in the room will be solid, but if you put it in your hands, it pools into a liquid. Your body temperature is enough to melt it. So if we did gallium, then it would melt, but it would be two separate liquids because the melted gallium would sink to the bottom. And so then like the calculation you're doing where you're mixing your two compounds and heating up everything at once,
they have different
CSPs. They have different heat capacities. And so all of those little tweaks would throw your system works great as long as we're doing water and ice. But if we throw any little tweaks into it, it might mess with your process. Whereas if we do this and eventually recreate your process, this allows better flexibility. Still works though, and if you do it on the exam, you'll still get credit because it's not wrong.
I have another question that has, if you want.
Let's do this one and then we'll get back to you again.
Yeah, so for the beginning part of the problem, would you recommend that new method of solving for n and like plugging it back into grams, or the old method of comparing the final, like the total change of energy of the water and the...
I kind of like the grams thing better. Whichever one works better for you, they both work, right? But I kind of like that grams thing better because it feels more like stoichiometry to me. And so I feel like it feels more familiar than the other things we've done. This is a problem that you'll see in physics classes as well eventually if you take, I think it's physics, I can't remember if it's physics 2 or physics 3 here, but you'll see problems like this with thermodynamics in them. And so that process of just thinking about the energy is very physics minded, but doing it in terms of like grams and amounts of material is very stoichiometry minded, so I think I like that better for this class.
Okay, thanks.
But either one works.
Thank you.
Betsy, yeah. And then your question?
It was like an ice question where the ice is past 60 degrees, or is past 0 degrees Celsius.
Is it the really hard one?
It's complex calories.
Yeah, that's the really hard one. Should we look at the really hard one? Questions about this before I erase it and we do the really hard one? Because your method doesn't work so great for the really hard one.
Yeah.
Okay. And then did you have any specific questions or are you just listening in for now?
Yeah, I had one question on it, but we can do that first.
Okay. What's your question? Let me just write it on the board so I don't forget.
I took a pic. I don't think it was from the homework. I was just studying with someone else and from a different class, but okay. It's like when like salt dissolves in water, it's kind of like the ice problem. It's like this kind of same thing with the delta H. I can read it later.
We'll look at it soon. Okay. So I just wanted a note on the board so I don't forget it. Okay, I'm gonna erase this, and then this is gonna be 3.1 something for the complex.
It's still 1.2.
Oh, it's 1.2. Which number is it?
14.
Okay. This one again. I think I have it in a different video, but I'm always happy to do problems again. So let's see what happens in this case. I'm like already bracing for it because I know how long this problem setup is.
One beaker contains 23 milliliters of 1.60 molarity HCl. and a second beaker contains 55 milliliters of a 0.40 molarity NaOH. Both solutions were initially at 20 degrees Celsius. We pour both beakers into a large insulated container which contains 5 grams of ice initially at negative 60 degrees Celsius. Calculate the final temperature of the resulting solution. The heat of neutralization is negative 57.3 kilojoules per mole.
It's a chemical pour over. Negative 57.6?
57.3.
7.3, thank you. Okay, so this is a lot. This is kind of like one of the hardest calorimetry problems I could think of. So, let's just do some bookkeeping to start. How many different Q's are going to be involved in this? Ooh, it's more than 4, but let's just start listing them. Which 4 are you thinking of? Or give me one of the 4 you're thinking of. Or is it okay? Don't worry. Okay. Who's got a Q?
Wait, is the question like you're mixing everything together?
Yeah. So we're gonna mix these 3 things together. We're gonna mix the HCl with the NaOH and the ice.
You're gonna have like a Q of the HCl losing heat, or like the reaction of HCl and NaOH.
And we're gonna have a Q of reaction. What's another one?
Q of the ice, like heating up to before it melts.
We're gonna have a Q of ice warming up. What's another one? We're gonna have a Q of ice melting.
Q of the 2 things becoming warmer, or like heating up, like the HCl would become colder. Sorry.
Cool. Yeah. So Q of reaction cooling. I don't want to call that reaction cooling.
Would you have to split it up into the Q of HCl cooling and the Q of NaOH, or after the reaction?
No, after the reaction, it's pretty much just like water.
Okay.
So we can just do Q of solution cooling. And then we've got one more.
Of the ice water heating?
Yeah. What I call the melt warm. Right, after the ice melts, it's going to warm up. So we end up with 5 different Q's in this problem. It's a lot of different Q's. In terms of how I frame my thinking, these 2 things are going to be my Q outs, right? Because the reaction is exothermic and the solution is warm and can cool off. These 3 things are going to be the Q in. And I can draw essentially 2 different pictures representing this. I'm going to have warm, melt, warm. And we have react and cool. And that's going to get me to some T final. Now technically, with this number of variables, I don't know if this is exactly how it's going to go. I don't know if this is going to be all my Q ins and all my Q outs. What if my reaction is so exothermic that it actually warms everything up? And so then I don't have that dipping down for my Q out. This Q solution cooling is actually going to warm up. That could happen. What if all the reaction in the water is not enough energy that the ice doesn't even finish warming up? That could happen. What if it warms up but then it doesn't melt all of the ice? There's lots of different variables. So my hunch is the best thing to do, all right, because like there's so many different choices, I'm just going to pick one and try it. I feel like this is most likely, given that the water's at 20 degrees, the ice is at negative 60, but there's only 5 grams of it, so there's not a lot of ice, even though it's cold. I'm going to do this. If my T final is below 0, I'm going to have stuff to deal with. I'm going to have to do this a different way. If my T final is above 20, that means I've got the wrong picture. I'm going to have to find some other way to do this. But I'm going to do this calculation and see how my T final comes out. And the way that I would consider this is I would essentially just calculate all the individual Q's and see how they add up together. Right? So I could say, what's the Q for all of my ice to warm up? What's the Q for all of my ice to melt? What's the Q for my reaction? And then the 2 parts that are the really variable part is this kind of thermal equilibrium part is the part that feels really variable to me. of like, where does the final temperature end up is the part that's weird. So let's calculate the 3 Qs that are a little bit easier to deal with. I'm going to erase this. I'm going to just put it here. Q, 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 Q. This is ice warm. This is ice melt. This is melt warm. This is solution cooling. This is reaction. Okay, and those are all Q's, not 9's. Okay, so there's all my Q's. I'm going to erase our thinking, and I'm just going to calculate the ones that I think are easier, that I'm a little bit more confident in. My Q reaction is going to be limiting reactant. Ooh, which one's the limiting reactant? I was hoping it would be obvious, and then I looked up and it's not as obvious as I thought. Oh no, I can tell still. The concentrations are 4 times difference. The volumes are only twice difference. So I think the 55 and 0.4 is going to be, the sodium hydroxide is going to be limiting. I'm going to double check by doing 55 times 0.4 is 22 versus 23 times 1.6 is 36. That one's bigger. So we're going to have 55 times
Do we need
0.4.
to write out their reaction to see if it's 1 to 1 or not?
We should if we can't already tell. I already can tell that sodium hydroxide with HCl is a 1-to-1 mole ratio. But if you can't tell that by looking at it, yeah, you should definitely write down the balanced reaction. The reason I know HCl plus NaOH is 1-to-1 is it's one of our most common strong acid, strong base reactions. It's just a really common one. The delta of this is going to be negative 57.3. That's going to give me my Q reaction. 55 times 0.4 divided by 1,000 times 57. Ooh, 3. I'm going to get negative 1.26 kilojoules. Another one that I feel pretty comfortable, so that's my reaction one, exothermic, as I expected. My Q of ice warming, I feel pretty confident about that one as well. That's going to be 5 grams. Oh, I need an equation sheet. Oh, good, I got one right here. I need the heat capacity for water in the solid phase, which is different than the 4.184 I remember. It's 2.1 times the final temperature is 0. The initial temperature is minus 60. All right, so I'm going to have a negative 60 there. I'm going to have 5 times 2.1 times 60. That's going to get me 630 joules of energy.
That's for the ice, like heating up to before it melts, right?
Yes, that's getting the ice from negative 60 up to 0 degrees. Only takes 630 joules of energy. Great. Then I'm going to go ahead and look at the Q of the ice melting. That's going to be 5 divided by 18 times 6.01. 5 divided by 18 times 6.01. That's going to get me 1.67 kilojoules. So if I looked at it with just these 3 bits, I would look at this and say, oh, look, I don't have enough energy from my exothermic reaction to melt the ice and to warm up the ice and melt it all. But my exothermic reaction is not the only source of my energy. I also have the water sitting at 20 degrees Celsius, which is above 0, so there's energy there that can be used, can be dissipated. So then I say, okay, we can do a consideration now of once I get up to this temperature, once I get here, does my warm water have enough? I'm going to do this just on my calculator real quick. I'm going to do 23 plus 55 to get my total mass of 78. I'm going to do times 4.184 times 20. So without the chemical reaction, just the warm water by itself has 6 kilojoules of energy to lose, 6.5 kilojoules of energy it could lose. So that warm water, the water at 20 degrees, is going to be more energy than all three of these put together. So it's not going to stay at 0. All the ice is going to warm up. All the ice is going to melt. And then that melt is going to warm up. Because, you know, the water itself, just the solutions, have a bunch of energy sitting at 20 degrees Celsius. If the solutions were sitting at 0 degrees Celsius, not all the ice would melt. But because the solutions are at 20 degrees Celsius, we get that extra energy. So now we can kind of set this up. I need to do Q of ice warming plus Q of ice melt plus MC delta T equals negative Q reaction plus MC delta T. Right, and the reason I'm labeling it this way is because I already did those calculations. I can just plug them in. So now I start plugging in the different bits that I know. My ice warming number, should I do it in, I'm going to do it in kilojoules, I think. Yeah, I'll do it in kilojoules. My ice warming is going to be 0.63 kilojoules. My ice melting is going to be 1.67 kilojoules. I'm not going to put the kilojoules label, just know that I'm doing everything in kilojoules. Plus 1.67. My MC delta T, this is for my ice, this is for my melt warming. So in that case, my M is just the 5 grams. My heat capacity is the 4.184. And my delta T is the part that I don't know. T final minus 0. Once my ice is all melted, it's sitting at 0 degrees, and now it has to warm up to some temperature that's above 0. Right? If this is my 0 point, that's 0 degrees Celsius, my solution is going to get warmer than that. That's going to be equal to my Q reaction, the negative Q reaction, which is going to be negative 1.26. Plus another MC delta T, but this MC delta T is for the solutions, not for the ice. Remember, there's two different things going on here. So that is going to be the 23 plus 55, that's 78. 78 times 4.184 times T final minus 20. Two things I have to do really carefully. Because I left everything else in kilojoules, I have to divide those two numbers by 1,000 to also get them in kilojoules. If I forgot to do that, I would have gotten a really weird answer. Be careful with your units. Be careful with your negative signs.
Is it not? Is the no.
So at this point, we're back to where we were before, right? This is now we're just doing algebra. I gotta multiply these together, FOIL them out, and I'm just doing algebra. I gotta multiply those together, FOIL it out. 5 times 4.184 gives me 20.9. FOIL it out, that gets me T final 0. So that's going to be 20.9 T final. Right, and then I can do the same thing over here. 78 times 4.184. Oh, I forgot to divide by 1,000, didn't I? I so did. Right, 5 times 4.184 divided by 1,000. Oh my goodness, I almost did the problem wrong again. 0.0209 T final. I can tell I'm getting tired. Weird recommendation. First a question. With show of fingers, how long are your study sessions typically? Is that like 3 hours?
Yeah,
3 hours, 5 hours? Okay, I'm usually like 1 or 2 hours. I usually need a lot of breaks. I need snacks, things like that. Before the final, you want to try to get a couple sessions of practicing doing problems for 3 hours. it's exhausting, right? Doing chemistry problems for 3 hours straight is rough. And that's what the final exam is. It's rough. But if we don't practice for that, it really hits us like a freight train when we do it for the first time. Okay? And I can tell offices are almost over because I'm about burnt out. So, but let's finish this out real quick. I'm going to FOIL this negative in. So this is going to be negative over here, positive over there. And I'm going to get 1.26 there. Then I'm going to have 78 times 4.184 divided by 1,000. That's going to get me minus 0.326t final. Plus, because I'm distributing that negative still, 6.52. Not 5.3 if I'm rounding properly. Right? That 6.53 kilojoules at the end, that's the amount of energy that the water has, that the solutions have because they're sitting at 20 degrees. They've got this bunch of energy just from water being at 20 degrees. I'm going to add this over, so I'm going to get something that's like 3.47. I'm going to subtract these over. I'm going to get some number. I'm going to divide. I'm going to get a t final. Let's finish it out. So we're going to do 0.0209 plus 0.326. I'm going to get, I don't know if this is even visible on the screen here. I'm going to get 0.347 t final is equal to 1.26 plus 6.53 minus 0.63 minus 1.67 is equal to 5.49. Do a little division, divide by 0.347. 15.8 degrees Celsius. This is also the point where I can slow down and I can check and I can say, hey, does that make sense? Is it above 0 and below 20? That's a good range. So it looks like a good answer. That is, again, one of the hardest calorimetry problems I could think of. So if you're like, wow, that was really hard, that is like too hard for the exam. It demonstrates a lot of complicated thinking, so I think it's worth doing, it's worth thinking through, right? That process of how do I consider the different cues? How do I approach this thing that's like got so many different complicated bits? Where are my assumptions okay? Where are they not okay? All of that thinking inside of this is really valuable. But way too hard for an exam. Well, not way too hard. More difficult than I would put on the exam.
The exam is only up till the end of week 4, right? Like not from what we learned like on Tuesday.
Correct. Up to the warm-up question we did Tuesday, because that was review.
Okay.
The warm-up question was like calculate the t where it switches from spontaneous to
Okay.
non-spontaneous. But then as soon as we started talking about concentration and equilibrium, none of that stuff.
Okay.
Questions about this problem? I think we got time for one more problem.
Okay,
Should
you
we
don't
do
have
your
to like
problem?
solve through the problem. I just have a.
Okay, I'm going to erase everything on here so we can at least get it. I like doing whole problems, though. Okay, you said this problem's coming from elsewhere.
Yeah.
Okay.
But it's like.
It wasn't off of like someone's quiz or exam, was it? It was just like a different homework problem?
Yeah. It was
Okay,
just, like,
cool.
different homeworks. Okay. A 5.2 gram sample of solid sodium hydroxide dissolves in 100 grams of water in a coffee cup calorimeter. The temperature rises from 23.6 degrees Celsius to 47.4 degrees Celsius. Calculate delta H for the solution process.
Wait, was it sodium hydroxide?
Yeah.
Huh. I didn't realize sodium hydroxide dissolving in water was exothermic. Where's sodium hydroxide?
Yeah, it says
Okay.
NaOH.
Yeah, that's it. Like I said, I just didn't realize that it was exothermic. How do I know it's exothermic? Temperature's going up. It's totally feasible that it's exothermic. The fact that it's exothermic, bringing back some of the things we talked about in the past, the fact that it's exothermic tells me the delta H of hydration is bigger than the delta H lattice. Right? So because it's exothermic, I can tell these other things about it. Right? This stuff really likes to interact with water more than it likes to interact with each other. Setup, right? So here we've got a calorimeter. We've got a temperature change. The fact that we've got a temperature change tells me I'm going to have some MC delta T. The fact that I've got this delta H solution as my question mark means I'm going to have some N delta H over here. Because the temperature is going up, the water is going to have an endothermic experience. This is going to have an exothermic experience. It doesn't matter which side you make negative, but I always like making the exothermic side negative. It just helps me keep things straight in my head. Now we start plugging in things we know. I've got 100. I've got 4.184. I've got...
That's what I was confused about, because in the work, like the answer sheet for, or like the worked through problem of this, it wasn't 100, it was 100 plus 5.2.
Oh, that would be more correct, right? Because it's got the total solution. The examples we've done in the past, we've always done like 0.5 grams and things like that. Let's see how it works out and see how big that mistake is.
It was off by like 5.
It's going to be about a
I had
5% error.
Like this, and like I kept getting like less kilojoules, and I searched it up, and like it was like way more, and I couldn't figure out why.
But
So,
I don't understand why you'd add them together if
they're not the same thing.
Yeah.
But keep in mind, and this gets into a detail idea, right? The temperature is increasing for the entire solution.
Okay, that's
So,
what I was confused about, because I thought it was just increasing for the water, and if it was just increasing for the water, you wouldn't add the masses together, right?
Correct. I agree with you. So this gets into some like nitty-gritty detail argument stuff that we can make. So I don't know where this question came from. I'm not gonna like get into it, but if we kept going, watch this. So we're gonna have 47.4 minus 23.6 is equal to 5.2 divided by 23, 24 plus 16 is 40, delta H. Right, so I would argue, and I think I would be fair to argue this, that if you include this as 105, this number shouldn't be 4.184 anymore, because it's not just water anymore.
Yeah.
It should be something that's a little bit larger or a little bit smaller, but I don't know what I would use for a sodium hydroxide solution.
Is it not aqueous? Like when we do like the other...
It is aqueous.
Like when
but,
we do the like chemicals, so we do it together, we use 4.184 because it's mostly water.
Because it's mostly water, right? So we could argue, so we have to make an approximation someplace. And the question becomes, where's the better approximation? If I approximate the mass of the solution to be 100, and I'm approximating this, I'm going to be making a mistake in that approximation. If the mass was small, and this is where we've gotten away with ignoring this mass before in other problems, when we've been doing aqueous solutions in aqueous solutions, we've been doing it in volumes. The mass of sodium hydroxide has been, if we calculate, we haven't had to calculate it out because we're mixing solutions, the mass of sodium hydroxide has been like 0.2 grams.
Okay.
Right?
So that wouldn't make that much.
And it doesn't make that much of a difference. Plus, we're doing it from volume. We'd have to do volume to mass. We're using the density of water. The density would be a little, there's all these places where it's like wiggling off a little bit.
Okay.
With a mass this large,
It makes more sense to do the mass, right?
yeah, right, and the cutoff is usually something that if it's more than a 2 to 3% error, we'd want to include it. So if this was only 2 grams of sodium hydroxide, I might be able to get away without including it still.
Okay.
But when it gets up to 5 grams, 6 grams, 7 grams, that's going to be important. Or you can imagine, if this was 20 milliliters of water and 5 grams, that mass you're adding in is a lot of extra mass.
Yeah.
Would this be something that's like on the midterm? Like,
I think if I did something like this on the midterm, I'd have to tell you specifically to make sure you include the total mass of solution.
Okay. But like if you're just adding adding something into water and it's like telling you the temperature change of the water, you wouldn't add the total masses together, right?
Well, here's the kind of tricky part of it. Can you get the temperature change of the water without the solid dissolved in it? Experimentally. No.
Okay.
Right? The ions are all floating around inside that water. It's gone aqueous.
Mm-hmm.
We can't really get the temperature of one thing without the other thing there.
Mm-hmm. Well, unless you're like putting hot metal in the water.
Right. So in the case of hot metal in the water,
you
yeah.
have to have them both together. Okay.
Yeah. In the case of hot metal in the water, they're completely separate phases. It's when something goes aqueous and we can't separate it out anymore. That's where it gets tricky.
Okay, but like on the midterm, it's not going to be a significant amount.
No, or I've put a specific note that says make sure you include the total mass of solution.
But then would you keep the 4.184 still?
Yeah.
Okay.
Right. So the 4.184, with that amount of sodium hydroxide going to the water, it might go to 4.19 or 4.20, less than a 3% error. Small change.
Okay.
Okay?
Yeah, thank
Cool.
you.
Okay. That's it for office hours.